Dear students, today we are going to continue with second module of advanced microprocessors and embedded systems. So let's go in detail. So here you can see the syllabus of second module. Over there we are having Intel 64-bit processors. Then we need to go in detail regarding the overview of 64-bit processor execution environment, memory organization, Intel architecture 32 memory models, memory organization in 64-bit mode, extended physical addressing in protected mode, basic program execution registers, operand addressing, multi-core architectures, and the concepts in power reduction techniques of processors. So as you can see in the previous video, we have covered till memory organization in 64-bit mode. So we will be proceeding with the rest of the portions. So here comes the first topic of this video, that is the extended physical addressing in protected mode. So when it comes with a sixth generation processor family, that is P6 family processors, where P6 indicates sixth generation processor family, the Intel architecture 32 Intel 32 architecture, it supports the addressing mode of 64 GB of physical memory, right? So whenever we try to execute a particular task, it is not trying to access the address space directly. So instead of that, what they are doing is it addresses the individual linear address with spaces of up to 4 GB. That 4 GB linear address space is being mapped into a 64 GB physical address space through a virtual memory management mechanism. This is what we explained in the memory management unit. Okay, so using this mechanism, an operating system can enable a program to switch from 4 GB linear address to 64 GB physical address space. And the use of extended physical addressing requires the processor to operate in protected mode and the operating system to provide a virtual memory management system. Okay, I hope you are able to grasp this. Okay, so what it is telling, whenever we try to access a memory, what it is doing, there will be a memory management unit. As you can see, there will be memory management unit, and this memory management unit, what it is doing, initially we'll be having a 4 GB of memory, that is the linear address space will be there. Here let it this be the let this be the linear address space. It is having 4 GB of memory, and this 4 GB of memory is being mapped to what? It is mapped to 64 GB of memory, that is the physical address space. Okay, this 4 GB is mapped to 64 GB of physical address space. That is done using a memory management unit. So using this memory management mapping mechanism, what an operating system can do, it can enable a program to switch from 4 GB to 64 GB. Okay, so and this particular process can be done under protected mode. Okay, and this is being done using memory management unit. That is a it will provide a virtual memory management system, that is meant by the extended physical addressing in protected mode. Next topic is basic program execution registers. Intel architecture 32, that is Intel 32 architecture, it provides 16 basic program execution registers for using general systems and application programming. And what are these registers? So let us see in detail. So there are general purpose registers are there. So there are 8 general purpose register which is available for storing operands and pointers. Then segment registers are there. These registers hold up to 6 segment selectors. Then E flags are also there, which indicates the program status and control registers. And the E flag registers reports on the status of program being executed and also allow limited application control of the processor. And also instruction pointer register is also there. It contains a 32-bit pointer to the next instruction to be executed. And here is the general system and application programming registers which we explained here. That is, there are altogether there are 16 registers are there. So these are the 8 general purpose registers. These are the corresponding segment registers, which are 6 segment registers, 1, 2, 3, 4, 5, and 6. And this is the program control and program status and control register. And this is the instruction pointers. So the same concepts which we have already studied regarding 803816 FOSS module. So this is regarding Intel processors. Coming to the general purpose registers. So here what we are doing, we are going in detail regarding the different registers what we are having. So here we took only the general purpose registers. So we are having a total of 8 general purpose registers. Okay, what are they? 1, 2, 3, 4, 5, 6, 7, and 8. These are the 8 general purpose register, which is of how many bit wide? 0 to 31. Altogether 32 bit general purpose, 32 bit wide, 8 general purpose registers are there, right? What are those registers? That is EAX, EBX, ECX, EDX, EBP, ESI, EDI, and ESP. Okay, so what is the purpose of using this general purpose registers? They are provided for holding the following items. What are they? Operands for logical as well as arithmetic operations. They hold the operands for arithmetic address calculations. They hold the operands for memory pointers also. Okay, now what this EAX, EBX, what this indicates? So EAX means it includes the accumulator for operands and result data. It is having 0 to 15, then 16 to 31. This is a lower and this is the upper one. And actually this is from 0 to 15, that is 16 bit. It consists of, we'll call it as AX. Okay. And this EAX indicates extended accumulator like that. Okay. And AX is 16 bit and EAX is 32 bit. And AX is further categorized into 88 bit, that is the lower one is AL, lower accumulator, and AH is the higher accumulator. Okay. Now the second one similar to this EBX. EBX is it point to data in the data segment. So it is having a similar set like AX. Okay, so accumulator. Next one is ECX. ECX is count. It is ECX indicates the counter for string as well as the loop operation. Over there also you can see 32-bit register, and here there are subcategories also which you can understand by seeing this diagram itself. Okay. Then comes EDX. What EDX indicates? It is the input output pointer. Okay. And then comes ESI. ESI is a pointer to data in the segment pointed by the DS register, source pointer for string operation. Then comes EDI. It is a pointer to data or destination in the segment pointed by the ES register, and it acts as a destination pointer for string operation. ESA acts as the source pointer for string operation, and EDI acts as the destination pointer for string operation. Then comes ESP, that is SP stands for stack pointer, that goes in the stack segment. Okay, and EBP corresponds to the pointer to data on the stack, that is in the stack segment itself. Here comes the general purpose register for 64-bit mode. So in 64-bit mode, there are 16 general purpose registers and the default operand size is 32 bits. So in the previous case, we discussed regarding IA32 architecture. Over there are 8 general purpose registers and we had discussed those things in detail. And the 64-bit registers, these general purpose registers in the 64-bit mode can work either with 32-bit or 64-bit operands. So that means they are backward compatible. If a 64-bit operand size is being specified along with the previous things, like in the previous case we had these registers along with certain extended registers also. So along with that, there are certain extra registers are also specified here like RX, RBX, RCX, RTX, RTI, RSI, RPP, RSP, and from R18 to R8 to R15. And this R8 to R15, they represent the 8 new general purpose register that is there in the 64-bit mode. What is this REX indicates? REX indicates it is the register extension prefix that is used to generate 64-bit operand size auto reference registers RA to R15. It is nothing but E indicates extended register, R indicates register extension, that's it. Then comes the limitation on accessing the byte registers in 64-bit mode. So in the 64-bit mode registers, we cannot mix the high bit registers AH, BH, CH and DH. These four registers we cannot mix with this SIL, DIL, BPL and corresponding RIP registers. But we can mix this lower byte registers with these registers. Okay, so why we can't mix this higher byte registers with this registers? Because there are certain encoding conflicts. While we can mix this high byte registers such as AL, BL, CL and DL with SIL, DIL, BPL and R8 registers. So whenever this rex prefix is used, the CPU disables. What happens is like whenever we are using this RAX prefix or this type of registers, whenever we try to use this type of registers, it will disable this four registers A, AH, BH, CH and DH, and it will enable AL, BL, CL and DL. Okay, so which can easily mix with the rest of the parameters. So that is why you can see here with rex AL, BL, CL, DL and the rest of the registers, byte registers. Okay. Then comes the segment register. The segment registers CS, DS, SS, ES, FS and GS. It holds a 16-bit segment selectors. And a segment selector is a special pointer that identifies a segment in memory. And to access a particular segment in memory, a segment selector for that segment selector must be present in the appropriate segment register. So let's see in detail. These code select, these are all things we have discussed in the previous module. Okay, so the base expansion of this terms are same as that of first, the use of segment registers for flat memory model. So we already explained what is meant by flat memory model. Different types of I-832 memory models are there, and among that first one is the flat memory model, then segmented model and hybrid model. We explained yesterday in yesterday's video, right? So this is the block diagram of a flat memory model. As you can see, in this flat memory model, we can see that there are different registers are there, code segment, all these things are there, which we explained previously. There are altogether 6 segments registers are there. So there are altogether 6 segment registers are there, and the entire linear address space for program has been uh, not at all segmented. That is why it is overlapped. That is why we are calling it as a flat memory model. That is unsegmented memory model. So when using the flat memory model or the unsegmented memory model, here the segment registers are loaded with segment selectors that points to overlapping segments. Code data as well as the stack. These segments are being overlapped here, and each of which will begin from the address 0. Okay, it will start from 0th address. And these overlapping segments, which that comprises of linear address space of the program. It contains the linear address space of the program, and uh, among the code selector segment register, it points to the code segment and all other segment registers points to the data and stack segment. Here CS corresponds to the code segment, code selector, and the CS segment it registers this particular CS segment register, it points to the code segment, and the all other segment registers, it points to either data or the stack segment depending on the need. Now come to the when it comes to the segment registers in segmented memory model. So as you can see, the entire linear space is being divided into code data and stack. Again, code data and stack. So whenever we use a segmented memory model, each segment register is ordinarily loaded with a different segment selector so that each segment register points to a different segment within the linear address space. So all segments are mapped to a same linear address space, and to access this, here the code data and stack has been segmented over there. So based on the requirement, this segment register what they are doing, it points to this code segment. It points to the code segment. So in the linear address space, and this data segment TS. So what it does, it points to the data segment as data segment, and then it comes to the another register, that is a stack segment. What it does, it points to the corresponding stack segments. Similarly, all these points are done according to the segment registers will point to the corresponding code, otherwise data, otherwise stack. This is a continuation of the previous slide. Here, as I already explained, each of the stack register, segment registers is associated with one of the three types of storage, either code data or stack. For example, the code register contains the segment selector for the code segment. CS, it corresponds to the code segment where the instructions is being executed and stored, and the processor fetch instruction from the code segment. What it is doing, the processor will fetch the data from the code segment using a logical address that consists of segment selector in the CS register and the contents in the EIP register. EIP register is nothing but instruction pointer register. So it points to the next instruction to be fetched. So that instruction is being fetched with a particular segment selector from the CS register itself. And this EIP register, it contains an offset within the code segment of the next instruction to be executed. It contains the data and it points to the next instruction to be executed. And this CS register, it cannot be loaded explicitly by any application program. So usually what they are doing, instead it is loaded implicitly by instructions or internal processor operations which change the program control, such as interrupt handling mechanism, procedure calls, task switching. So using this mechanisms only, they will be changing the corresponding application program. Okay, loading those things. So this is a segment register in 64-bit mode. In 64-bit mode, code segment, data segment, and this ESSs are treated as if each segment base is 0, regardless of the value of associated segment descriptor base. And this creates a flat address space for code data and stack. And both segment registers may be used as additional base register in linear address calculation. Even though segmentation is generally disabled, the segment register loads may cause the processor to perform segment access assist. And during these activities, enabled processor will still perform most of the legacy checks on the loaded value. And such checks are needed because a segment register loaded in 64-bit mode may be used by an application running in compatibility mode, and limited checks for this registers are disabled in limit checks for this are disabled in 64-bit mode. Next come the E flag registers. So as you can see, these are the flag registers. It is somewhat similar to what we explained in the previous module itself. Here there are different flags are there which are of 32 bits. CF corresponds to carry flag, then PF corresponds to parity flag, AF corresponds to auxiliary carry flag, then ZF corresponds to zero flag, then SF corresponds to sign flag, Then comes TF, it corresponds to draft flag. Then IF corresponds to interrupt enabled flag. DF corresponds to direction flag. OF is the overflow flag. You can see all these things. You can go through this. Okay. And the corresponding actually this is used for accessing the different status or indicating the different status of various programming types. Okay, so you please go through in detail. So we'll go with the next slide. As you saw in the previous slide, there are various flag registers are there. So E flag means extended flag. Okay, so different types of flags are there, like status control system flags are there. We'll first take the status flag. Basically, there are three flags: status flag, control flag, and system flag. So we will explain with the status flag. So among the 32-bit flags, the various status flags are CF. CF stands for carry flag, and PF is the parity flag, AF is the adjust flag, ZF zero flag, SF sign flag, and OF is the overflow flag. So CF means it is corresponds to the bit 0. Okay, and this is a carry flag, and it is set if an arithmetic operation generates a carry or borrow out of the most significant bit. Okay, so I think you might have studied all these concepts in the previous semesters. So carry flag is used to indicate whenever there is a carry generated. Now, parity flag, that is a bit number 2. This is bit number 0, 1, this is 2. And parity flag, it is used to indicate whenever there is whenever the result contain any even number of ones. Okay. Otherwise, this parity flag is 0. If there are even number of ones, then it indicates if the LSB contains even number of ones, parity, then it is 1. Otherwise, it is cleared. That means it is 0 is the A flag, that is the adjusted flag, and this is set, that is it is set to 1 if an arithmetic operation generates a carry or borrow out of bit 3 of the result. Okay, otherwise it is 0. That mainly occurs in the case of BCD arithmetic, which you studied in digital electronics. Okay, then comes 0 flag. Whenever the result is set to 0, whenever we get a result 0 during calculation arithmetic operation, then the 0 flag is set, otherwise it is 0. Similarly, sign flag, it indicates the sign bit of the signed integer. So whenever there is a signed integer, it is set to 1, otherwise 0. Overflow flag, similarly we can explain this. Okay, among this status flag, only the CF flag can be modified directly using STC, CLC and CMC instructions. The other flags cannot be modified directly. So how the CF flag can be modified? It can be modified using certain instructions such as STC, that is set carry flag, CLC, that is clear carry flag, CMC, that is complement carry flag. Okay, so in this way we can modify the carry flag. And here the table shows the effect of CF flag when using these instructions. Also the bit instructions BT, BTS, BTR and BTC codified bit into the CF flag. What is this corresponding BT? It is bit test. BTS is the bit test and set. BTR, bit test and reset. BTC, bit test and complement. T stands for test and S stands for set and C stands for complement. So the table shows what it does to the bit and what it does to the carry flag. So how a carry flag will be changed using these instructions. So among the status flag, there is one flag, like there is a direction flag. So that is the 10th bit of the extended flag register. And what it does is it controls the string instructions like MOVs, moves, CMPs, SCAs, loads, stores. And setting the DF flag, direction flag, causes the string instruction to auto decrement. And clearing the DF flag causes a string instruction to auto increment. That is the reverse of this. And STD and CLD instructions are used to set and clear the DF flag. You have to be just aware of these concepts, right? Then comes the system flag and IOPL field. The system flag and IOPL field in the E flag register control operating systems and executive operations, and they should be modified by application programs. And the function of each flag is shown in this figure. Okay, different types of flags are the TF flag, that is a drive flag, that is bit 8, and till bit 21 it is written here. So please go through it. So you have to be just aware of what is meant by TF flag, IF flag, IOPL, NT flag, virtual 8084, 8086 mode flag. All these things you have to be just aware of this. Okay. Then comes the R flag registers in 64-bit mode. So in 64-bit mode, extended flag register E flags is extended to 64-bit and are known as R flag. Okay, register extended. And the upper 32 bits of R flag is preserved and the lower 32 bits of R flag is same as the E flags. Instruction pointer. So the instruction pointer, which is known as EIP register, it contains the offset in the current code segment for the next instruction to be executed. And the EIP register cannot be accessed directly by software. So we have to control this by certain control transfer instructions such as jump, JCC, call, return, like interrupt and other exceptions. And the only way to read this instruction pointer is to execute a call instruction and then read the value of the return instruction pointer from the procedure stack. So in this way only we can directly access this IP register. Okay, EIP register. And the EIP register can be loaded indirectly by modifying the value of return instruction pointer on the procedure stack and returning a return and executing a return instruction that we already discussed. We can't directly access this instruction pointer. So in order to access this register, what we have to do? We have to use certain instructions to access those things. Now, when it comes to the instruction pointer in 64-bit mode, in 64-bit mode, the instruction pointer register becomes the instruction RIP becomes the instruction pointer. And this register holds a 64-bit offset for the next instruction to be executed. Previously, it has the 32-bit offset. Now it is having 64-bit offset. Why? We are discussing regarding 64-bit mode, right? And the 64-bit mode also support a technique known as RIP relative addressing. That is register instruction process, register extended instruction pointer, relative addressing. And using this technique, the effective address is being determined by adding a displacement to the RIP of the next instruction. So this is regarding instruction pointer.